Okay. Okay. All right. So, so these are some of the kind of anecdotes that keep coming. I will share with you. Okay. In the coming days as well, just to light up the mood, give you motivation. Uh, what we are trying to learn. Okay, so this we said again in the boot camp. So we did the Gen AI. What about the basics about LLMs and prompt engineering? So we'll continue with a part of LLM today and move on to embedding models and vector search, vector databases. Um, and then tomorrow, slowly today and tomorrow, we will continue in this with the hands-on lab, mostly tomorrow, if we can get today or continue into tomorrow. And then we will plan these in the coming days. Okay. So we looked at it yesterday. I know I didn't want to do slides today. I want to get into the demo straight away. But as I started exploring, I thought, no, definitely we need to first understand, talk about this, get some clarity, get into the demo. It'll be more easier for us. So you have to bear with me at least for the first half of the discussion today, that we will be going through some of the concepts and terminology that is very important, because this is the basic of all LLMs, RAGs, agentic AI, whatever you do. This is like core. Okay. So you have to understand and have your knowledge of how all of these things work, and what is the terminology, what does embedding mean, what does vector search mean, what does semantic search means, how do you use that, what is a chunk, what are the strategies and all of this. So these are some kind of terminology you should be aware of when you talk about the Gen AI. So we at a high level, we said any LLM, for example, like ChatGPT, you are a user, you ask a question, which we call a prompt in the Gen AI world, and then it provides a response. This is at the very basic level, right? Now, what happens inside this is this. Okay. I want to write this. Okay. See on the left side, you see what happens. The user asks or gives a prompt. The input is interpreted. It understands the context, search for the best response. This is basically within the LLM, and the answer is crafted or edited or put it in the proper language, and then it is published. Responses published. Now, if you look at what goes on inside this, is when the user gives the input, it is basically split into the tokens. So these are the words that are mostly used in the GenAI world. You should get used to using these terminology. I mean, when you go to any of the interviews, so you should be very comfortable using this language: tokens, embeddings, semantic search, and vector database. So you should throw all of these terminology, so that the person knows, hey, this guy knows what he's talking about. Okay. So a token is nothing. It's just all of them are different words. Like you said, a question is a prompt in GenAI world. A word is a token in the GenAI world. A token means it can be a word, or sometimes it can be a paragraph or a sentence or whatever it is. It just can say a group of input. It's split into tokens. So this tokenized input is passed to an embedding model. Now, what an embedding model? We'll talk about it. So it's an embedding model. So it gets an embedded tokens. So the tokens are converted into embeddings and the tokens. It gets contextual embeddings inside it again, and then it gets the response, generated response draft from it, decoding. So this is encoding and decoding from embedding and back to text, then refined and polished, and then the response is sent to the user. The same thing. So this is what happens inside technically. But yeah, you don't have to know all of this, just for your understanding. You don't have to memorize or know all of this, but for your understanding, to know what goes on behind this. Okay. Okay. So what does it happen within the LLM, right? We talked about yesterday a large language model, and we said it is trained on massive data, right? On the books, on the text that is on the internet, on graphs, chats, whatever it is. So what this is what all about the LLM model is. So it has all this data that is ingested, cleansing, deduplication, all that happens. And then this is the tokenization. What does the tokenization mean? Splitting of these text into chunks or words, and each word has some kind of a notation, number notation. Then each token is converted into embeddings. See here, man, woman, king, queen, for example. So this is a different text. So forget about this text. It's just showing how it is split into the tokens. Now these are called vectors. A vector is a collection of say different dimensions, 2 dimension, 3 dimension, n dimension vectors, collection of numbers, okay, arrays. So a word man is converted into a vector of these numbers. So the machine interprets and represents man as a set of these numbers. So this is a vector. How many dimensions? 1, 2, 3, 4, 5, 6, 7 dimensions are shown here, but it is just an example. I will show you each embedding model has a different dimensions that it uses, 1024, 1500 or 2000, whatever dimensions, which means that it is represented in so many dimensions. I mean, collection of so many numbers. So if it is 1024 dimension, a word, just a word man is converted into 1024 numbers in a vector like this. So woman has something like this, king has something like this, and queen has something like this, all these 4 words. Now, in a n-dimensional world, these are how they are mapped based on these vectors. So in the n-dimensional space, it's not a 2-dimensional space, it's an n-dimensional space. These words are actually placed like this based on the vectors that it is generated. Okay. Now, why are they placed here? Because when you search, we'll talk about the semantic search. It looks for what is the closest to the given token, okay, or given vector. The token is again converted to vector. Suppose a woman is closer to the queen in the n-dimensional space than to a man or to a king. Okay, king is again closer to a space in the space to man than a woman. Okay, so something like that. It all in the n-dimensional space they are placed, and a semantic search uses the cosine similarity. There are different algorithms to search for the nearest neighbors and give you the results. Okay, so we will come to that. And then you have transformer layers and parameters, everything, which will crunch these numbers to understand what is the input and what is the output based on these vectors. So this is how the LLMs are trained on the data set, okay, at high level. Now, let's see what happens for the same large language model. I have given an input saying that not all heroes. Okay. Now, the task of the large language model, as we discussed yesterday, is to predict the next token or the next word, correct? And then we have seen it goes through all of this neural network analysis of the input and what it is learned, what it has. Sample take token from vocabulary it already has. And it has seen some kind of pattern like this was always followed by a few words. Sometimes it has come with man, sometimes it has come with woman, sometimes with cape, sometimes with bread, sometimes where. Now, when it take this entire input and converted into a vector and searched with the other words, the closest one it came with is the highest probability is 0.07 is where. So it deducted that where is the word that will come. It predicts that where is the word that is most likely or most probable to come after the heroes. So not all heroes were, and then the next probable is 0.06 is K. So heroes were K. Now it generated the text, not all heroes. The next word it predicted where, the next word it predicted K. So that's how the generative AI models predict the next token and generate the text. Okay, again, this is how all of this is how the LLMs, work internally. You just have to know the high level knowledge of this. Okay, so any questions on this? Guys, please.
So, Harun, I have a question
Yeah.
here. So here the LLM is basically predicting the next words,
Yeah, tokens.
next tokens.
Yes.
So what we are seeing in Chat GPT is much more added to this, right? Like, I mean, it's not just predicting the next words. In addition to that, lot other functionality is also happening behind the scenes, right?
Yes, yes, definitely. So this is the underlying algorithm, the transformer model that on which all the GenAI is built. The basic algorithm is it works attention is all you need. The paper that came out in 2017, it's talked about like predicting the next token, the probabilities. But this is
Okay.
just one of the algorithms that it was built. I mean, yeah, you're right. It's not LLM is not just predicting the next token, but that's how it works. It starts, the algorithm is used to generate the text. But
Okay.
yes, a lot of other inbuilt logic or machine learning that happens because you're not just completing the sentences, right? So you're asking the LLM sometimes to summarize the document. So these are all different tasks. Okay. But this is the basic of how the LLM started building, the algorithms to predict the next token.
Okay. Okay. Yeah.
Okay. Okay. So we've seen this in this, right? So LLM is here. Now we looked at what happens, how the LLM is all of this is done. And then we also saw yesterday all of this, whatever we have seen, it is trained on is static. And then we looked at it does not have information about the current data, which is published after the model was published, sorry, which happened events after the model has published, because it does not know, it was not trained on that data. So it has to connect to the internet or external sources to get that data if you want to know anything about the events that happened after the model is published. Correct? The second point we discussed was it does not have information about personal data or my organization, whatever I have, private data, which is so let's say my company has my financial data. It's not in public. So the LLM does not know and it cannot answer questions about my company's revenue or my company's product design or details or whatever formula, which is not public, right? Unless I publish my annual results out, and then it can read from the next net and answer those questions on that. But if it is private, it does not know, right? So these are the two things we discussed yesterday. So this LLM here, it has the information, whatever it has when it was trained. Now to augment it, to add the data to it, we are adding our own data. Let's say my company data I want to add, or my service manuals I have. I want to add that knowledge to the LLM to answer the user's question. So here I have my database, which has user manual PDFs. I will take those PDFs, split it, store it in a vector store. Again, here somewhere, when I split, before I put into vector store, I will generate the embeddings and put it in the vector store. And when I use the query, it will go to vector store and get the relevant data or relevant records, relevant splits, relevant blocks of text that is closer to this question. And then this entire relevant information is passed to the LLM with the question and the relevant data both. So the LLM then will read the question and the data that has come in with the prompt and build the answer and then give it out the answer from that relevant data, because that is my company data. Okay, so this is the
So,
rack.
so basically, we are telling the LLM to read all the relevant sections and then answer. We are providing the relevant data from our
Yes.
company
For
data.
example, in this query, right? Sometimes in SQL we give hints. So similarly, we give the LLM, hey, this is the question, and these are the possible um, relevant chunks of data where you can find answers. So go through all of these relevant data and then answer the question. That is what we are asking the LLM to do. Okay, so if it has its own proprietary knowledge, okay, you just want to know something about, hey, tell me about Einstein. It already has all the knowledge about Einstein. It will give you 10 pages or 100 pages, whatever you want. Okay, that's fine. Now, if I want to say, hey, what is the sales data of my company in the last, say, last quarter? So the quarter results I have not, or last 1 month. So I have not published, or say my company is not public, so I don't need to publish. So that data LLM does not have, it doesn't know. So in that case, what I will do, I will connect the data, or in this case, it might be a Word document, or it might be, say, a database actually, where you can create a SQL query again as an agent or a tool, and then the agent will use the tool to get that information from the database and pass it to the LLM. Hey, so here is the data and here is the question. You go ahead and prepare an answer and publish it.
Arun, for this vector
Oh,
store, what kind of storages are mostly used?
Sorry, Emma, you are not audible. Can you be a little louder?
So for this vector store, right,
Mhm.
what type of storage is expected? Can it be in memory or file or something like that, or do we need a strong data storage like SQL, NoSQL databases?
Yeah, so there are vector stores available, vector databases. You use one of those vector databases. Okay. Now they can be in memory, they can be on the cloud, they can be on-prem, just like your SQL databases. These are same, like we will talk about those. So these are just the databases which have capabilities to store a vector and to do a semantic search on the vectors. So what are the examples? From Meta, we have a FISDB, Facebook AI semantic search database. So that is a document-based database. Now you know the Postgres, right? PG. Postgres has a vector database called PG Vector.
Oh.
Then you have Pinecone. Pinecone is a vector database. Then you have Chroma. Then you have AstraDB, which is a version of Cassandra. Okay, so there are so many. We'll go through it. I will walk you through. We will do some hands-on also on those vector databases, um, creating this. But yeah, vector store is a separate vector database that you need to use, create so as a service.
For a small learning model, right, do we really have to use vector store or can we do it
It,
in
it
memory?
doesn't matter if your LLM is small or big. It depends on, even if your data is small, you can use a small vector store, just like ChromaDB is a very small cloud-based small database. or you can go FileDB, which is document based. You can actually create volumes on your server and then use it as a vector database.
Okay, got it.
Yeah.
Uh,
So if you need big ones, you have huge data, then you go for PG vector or you go for Pinecone. So it's again, based on your use case, how fast and how effective your retrieval need to be. What is the volume of the data you are processing or chunking? How many user requests that you are processing per second? So all of these will, give dictate your what kind of data store. Again, when you have a vector store, you can also have some in cache. So frequently used queries, you can run it and then cache those results in a cache DB also in between. And then again, you can enable the cache, go to the cache. If it does not have, then go to the vector store, all that you can build. Yes, Pawan.
So Harun, again, here the question we discussed yesterday becomes relevant, right? Because we are sending relevant speeds from our, say, from our company's data to the LLM. So we are giving the data to LLM. So uh, will there be any kind of security enforced there so that the LLM doesn't keep it after processing the data?
Yes, obviously. It will not store your data. See, again, so it's all LLM is also more like your cloud. So now if you have a cloud database, you also have virtual private network, right? Amazon, you can have cloud, or you can have virtual private cloud. Azure, you can have virtual private cloud. So all the banking and financial systems, they put on the cloud, but the cloud is actually private. Nobody, it does not have anybody, other people does not have access to the cloud. So it is secluded from the other cloud, and it is dedicated to that particular customer. So that kind of security. The same thing happens here. Your LLM can be a foundation model where it can be paper token model, which is like, LLM somebody is hosting. For example, AWS Bedrock. AWS is hosting some model, LLM model. You don't buy it, or you don't install it, or whatever you do. You use that LLM as a paper token model. So what you do, your question, you send it to the LLM as an API. Now the LLM will send you response in the API. So each API call will be charged, like how much data you sent to the LLM and how much data the LLM sent you back. Again, we are talking about the tokens. So based on number of tokens you sent, okay, ingress, and number of tokens LLM sent you back, egress. So based on that, it is charged. So we can see that also. If you go to Amazon Bedrock and look at the models, it will show you how much it will cost you when you use that model. Each model, when you are talking to it, when you are sending your data to it, how much it costs. Now all the security of Amazon AWS, just like your cloud database, what you have. So your data is already on the cloud. The same security will also apply to your LLM. Okay, that's one thing. Second, you can always choose to host your LLM on-prem. Get that LLM model and host it on your premises and use it locally. That is also another model. So it's based on use case, how much security you need, what security you need. It's not a new thing, right? It's already,
Okay.
most of your data is already on the cloud. So it's no different. So it will be same. But yesterday somebody asked, right? So if we give something to LLM, will it be available to entire world? No, it's more like an instance that is given to you. So what you give it to LLM, it will only remember on your instance. Okay, it's not a class. It's kind of an instance. If you go into Java world, whatever you set the properties to that instance will live only until that instance is live. Somebody else is creating another instance from the class. You get only default features of that class, not that something you have put in the new in your instance, right? So it's a copy of the LLM that is published. Okay.
Yeah. Okay, sir. Thank you.
All right.
Yes, sir.
Good questions. Yeah.
Yeah, The document loading, right, in the section, a database section, can it be any database, relational or non-relational? Or
Yes,
in this sense?
it can be a database, it can be a file store, it can be
Okay.
S3, it can be Azure. It is just an ingestion. You are getting a document, I don't care where I'm getting the document from. Okay, it may not be document at all, as I said, right? It can be a SQL, it can be a database. You can actually getting the records from the database and then storing in the vector store. That is also a kind of valid scenario.
Yeah.
Okay. Okay. So another representation, it's basically the same, as I said, same thing represented differently. So go with the sequence number 1. User sends a query. Okay. Query is embedded. Okay. First, before going here, let's go here from this end. Data preparation, raw data sources. That's what we looked at, the files. You extract the information from this OCR, PDF data extraction, or web crawlers. You want to get the data from the websites, whatever it is, you read the data, you do chunking. Okay, you split into chunks, pass it to embedding model, generate the embeddings for each chunk, and that embeddings are stored in the vector database. So this is all, the left side of it is your data preparation. The right side of it is your RAG. This is ongoing. So when user gives a query, that query is also sent to the same embedding model, and then that is converted into an embedding. And that vector is used to search in the database to get matches with the query. What are all the chunks that are matching with the query? In the response, you get all the records that are matching, all the chunks that are matching with this user query, and that is passed to the LLM, the query and the relevant data. Now the LLM will crunch that data for the query and generate a response and give it the response. So this is the entire RAG. So today we will be discussing about the left part or some of the top part. We don't go into relevant data and LLMs today. We will go after, vector database. We'll go into RAG, then we will complete this cycle. Okay, any questions on this? You guys see, everybody, this is like, in ETL, if you say, what do you think? Extract, transform, load. On the left side, you have databases that you ingest. Then the middle layer is transformations you write, and the right side is loading into database. When you come to GenAI, this is the blueprint that you have to memorize and think about immediately. Data ingestion, chunking, embedding, vector database, query, embedding, relevant data, LLM response.
So we can call it as a high-level architecture, something, Arun?
Yes, this is the RAG flow. Okay, architecture for a RAG. Now here, the LLMs will change. Okay, you can choose any of the LLMs, like hundreds of LLMs. You can choose any of the LLM. Again, based on which LLM is costing you less pay per token, or which LLM is trained, or you want a domain-specific LLM, you want large or you want small. All that based on, you can choose any LLM. Embedding models, again, you can choose any of the embedding models out there based on what you need, how much depth you need. You need a vector dimensions of 1,000, 2,000, 3,000, whatever. And then what is the context window of the LLM here? So all of those features that you have to use when you choose the embedding model and the LLM. But the only caveat here is whatever embedding you use here, the same embedding you have to use here. Only then you will get the relevant results. It's like comparing apples to apples. Okay, if you generate embedding with one model and you are searching with the embedding generated from another model, they may not actually get you good results, right? So basically what you are encoding with the embedding, you have to use the same model to decode and search for the vector database. That's the one rule that you have to follow, remember. And your vector database should actually be compatible with the dimensions of what the embedding model is generating. So if embedding model is generating 1024 dimensions, when you create your vector database or schema, whatever collection, you should also match that dimension. that, okay, whatever vectors I'm storing here will have a dimension of that same number. If they don't match, it will throw error. So these are the two things that you have to remember while doing embedding and vector databases. Now with that, before getting on to the vector databases, we'll do a time check. Okay, okay. What is a non-semantic search or a normal search, right? In a SQL, if you go and do a SQL search, let's say the question is, where is the World Cup? Okay, and the possible responses are these four. Why? In a non-semantic search, if you have a plain SQL, this is again non-semantic, but if you just do a SQL search, what you can do, you can either match with the entire question, or you put where clause like percent, all of this sentence, or like any of the keyword. But that will only give you, if you put word, percent word, so wherever it is word, only it will give you those. That's the first level. The second level of non-semantic search, it's more like how Google does the search is, it will take all of these words and do count of how many are matching with the target. So if you say, where is the World Cup? There are 5 words here. And if you see in the responses, the first one, World Cup is in Qatar, is 4 words. Okay, World Cup, okay, is and the. So all of these words, they count. And the next one is 2, next one is 2, and next one is 1. Okay, apple is a fruit. So this is how the non-semantic search works. Okay, but if it says, if I put a question which has same words but a different meaning, okay, where in the world is my coffee cup? So that has nothing to do with the World Cup we are talking about. The context is completely different, right? But then since the number of words are matching, if you ask, hey, where in the world is my coffee cup, it will give you the World Cup is in Qatar, right? So that's how the context is missing when you do the search. That is a non-semantic search. Now, when you do semantic search, what it does is it basically puts in a vector space. Now, we talked about number of embeddings, right? So how does the embeddings impact the search when you search for something? Now, I have these sentences. The bear lives in the woods. The World Cup is in Qatar. The apple is a fruit. Sky is blue. So each of them have separate embeddings. And when you map those embeddings here, so they are in different spaces in the plane. For convenience, we are seeing it here in the 2-dimensional. As I said, it is again depending on the vector dimensions. Might be 1,000, 2,000, whatever it is. Now the bear is here. The cloud is here, some representation. Okay, but this is not, it will not be stored as pictures, it will just be numbers. When you do the query, where is the World Cup, based on the embeddings generated, it will be placed here. So if you see, it is closer to this one, which is the World Cup is in Qatar. That's how the embeddings and the context is. So when you search for a response, the closest one will be this. So where does the bear live? If you ask this question, if you convert this into embedding, where does that fall, this query? On the plane?
On top right side, right?
Top right, yeah. So where the bear is. So it will be somewhere closer to that. And what color is the sky will fall somewhere top left. And what is an apple will fall somewhere on the bottom right. So that's how the embeddings are done. So if you see here, the question and answers, the blue dots, that's where they fall in the 2-dimensional space. But this is again at the high level. I mean, don't take it literally. It will be like this in the graph in the 2-dimensional. It's just for graphical representation to understand how semantic search works. Okay. Now, based on the question, the closest one is what you get the answer, right? Now look at this, distances. from one question to other answers. Okay. So if the red line, where is the World Cup, right? So first it will get the answers for all the dimensions there. So the World Cup is in Qatar, the distance is less. Okay. The bear lives in the woods is far away. And then apple is far away and the color is far away. So based on those distances, it will give you the response. Hey, this is your closest answer. Semantic search. Okay. So this is the representation. Now, how does this work in the actual database? What are the things that we need to get this semantic search working? I will show you. Okay. So before that, quickly we'll go here. I don't know if this is, oh man. We have to start again. Okay. Let the cluster start. I will go back and show you some, how the dimensions are for that stuff. And we'll come back here. Okay. Okay. So meanwhile, by the time the cluster is up, let's go back and review. So I know I will do multiple reviews so that, the concepts are very clear. You should be very comfortable with all of these concepts. Okay. Any questions, observations? Anshu? Oh, Anshu, I think he's driving, is still driving maybe. Hema?
Yeah, she said she cannot continue. So the near neighbor search,
Mhm.
are there different models for that also?
Different models in the sense?
So identifying the near neighbors. Do we
Yeah,
have?
so there are different algorithms. Yes, you're right. There is a cosine similarity search is what is the famous one that is used. It's called cosine similarity
Okay.
based on the distances. But I think there are some others we'll have to look up for the semantic search, nearest neighbors. When you Mm. Okay, not here. Let me go and see. Usage. Okay. This. There is one second. Let me check where that is. This is the database. And then connection. Create collection. Okay. See here. When you create a collection in the database, right? So you give the embedding generation method, what model you are using to generate the embedding. You also give what is the dimensions that is created. And you also give what is the similarity metric that you want, method used to calculate vector similarities. So there is this cosine similarity, dot product, Euclidean distance. These are the three methods available.
Got it.
Okay. Yeah, you can choose any one of them, but default it uses cosine. Okay, we'll come. Yeah, Pavan, tell me.
Is it like the number of dimensions we use? Is it directly proportional to the quality of results we get?
Might be. Okay, if you see here,
How much they will be charging for 14 GB 4 cores?
I'm sure, but normally not much if you're not using, but I have seen my cost go up from $30 per month to $140 per month. Okay, so these, if you see, these are all the text. This is what we call chunks. Okay, the document is split into these chunks. Okay, paragraphs or sentences based on the size, how much I want. And if I look at the embeddings that I generated for this, so it will show you here. This is the ID. This is the text. Okay, so this is the complete text. And for this text, this is the vector that it has generated. Now, if you see here, this vector, you see how many elements are there in this array, vector array. So this is 1024, I believe. Okay, 1023, since it starts with 0, it is 1024 elements in the array. So basically, each chunk is converted into a vector of dimensions 1024. So this is how it's. So all of this text here is somehow being represented by that vector. This entire text is represented by this set of numbers, this array of numbers. So this is how the embedding works. And this is how you store the data in a vector database. Okay, now come back. So if it is 1500 or it is 3000, based on that, you will get the number of elements in this array, in the vector. Now come back here. This. So more of this. Just give me 1 second. My laptop is dying. Let me get the charger. Give me 2 minutes. Okay, all right. So we are getting into a few more slides of terminology, basically on what we have seen on the vector databases. Then we will go into detail looking at the use case demo. Before going here, any questions on what we have just discussed, or we are good? Can move forward. Yes, Pawan.
So, Harun, can you go back to the previous screen where the chunk is mapped to the vectors? So, is that chunk size is it predefined or like is that also configurable?
It
Like
is
I mean,
it is configurable.
oh, okay.
That is what exactly what we are seeing here, chunking. Okay.
Oh, okay.
So you can give what is your chunk size. So basically, so I have like 6 slides. Okay. So what is a chunking? We have seen, right? So chunking is basically splitting the data into smaller parts. I don't want the entire document or entire research paper if I have 20 pages and then all dump it at one place, generate an embedding. And when I search any question, it will give you the entire document, 20-page document. So then there is no point in having that, right? So there is no, the purpose is defeated. So what we do is chunking refers to breaking. Chunk, its term itself says, it's chunks, breaking into smaller chunks. Breaking larger pieces of data, documents, articles into smaller manageable parts for efficient processing by AI models. So that is what you call chunking. So why is it necessary? LLMs have token limits, making it essential to process information in smaller chunks. So what is the token limits? As I said, like token is number of words or information that you can send to the LLM. So each LLM will have some token limit that you send it toward. It cannot handle MBs or GBs of data at a time. So that's why you have to, first thing is that you have to limit your tokens. Second, most of the models also have a pay per token model. So then if you're not efficiently chunking your data, you're just sending the entire document or chunk or junk data, entire data to the LLM. So it will count all the tokens and then charge you. For everything your 20 page, if 10 questions you ask, 10 times you are sending the entire 20-page document, you will be charged 20 times. Okay. If you properly chunk it based on, say, headings or sections or subsections, whatever it is, then your question will only send those relevant subsections to the LLM to go through and give the proper answer. So one, you are handling the token limits, two, you are handling the price, and it is more efficient. The more data you throw at it, the more data it will give you back in the response, right? So it has to be focused. And it improves context relevance in downstream tasks like search or retrieval. When you do a search or retrieval, it will improve the context relevance. Okay, so you ask for, let's say, a company HR policy document. Okay, and then you want to know what is the maternity leave policy. Then if you are sending the entire HR policy documents to the LLM, it has to go through the entire document, read it, figure out, find it. Instead, if you split it by each policy, and then you send only relevant 2 or 3 where that word, maternity comes in, and send it to the LLM, it will go through that and prepare and give you an answer. Okay. So that is the example 20-page research paper into smaller paragraphs and embed each section separate. And if a scenario is long legal documents, instead of processing the entire document, you can chunk into clauses or sections in that legal document focused on specific legal terms, whatever you need. Now, what is the downside of it? So basically, if you split, the upper part may not know what is in the lower section. So these may be two disjoint things, though they are related to each other. Okay. So for that, you also need to define a overlap. So that we also talk about. What are the strategies for chunking? You can do based on length, token or words, logical sections, semantic meaning. So however you want to split, you can split. So this is again, it's not something an LLM or RAG or whatever. This is something you have to implement how you want to do the chunking based on your data. And this is pure, again, you can use a Python, use the Python libraries available like PyPDF that is used, or text splitter. Those can be used to split the text in a text file or the PDF file, something like that. Key factors to consider again, token limits, logical flow of content, and overlap if required. So overlap is basically, again, you can see, let me go back here and see. What is the last line here? Do not attempt to extinguish an oil, grease, etc. Blah, blah, blah. Right? Now, okay. Okay, maybe, but sometimes. Okay, so what happens is when you give an overlap of say 100 characters or whatever, the last line is repeated. Basically, this will be at the end of this chunk, and the same line will start in the next chunk. It will repeat in the start, so that there is a overlap between these two chunks. So that will help you understand that these are the sections that are next to each other. It's a logical flow of these sections. So that can be maintained using the overlap in the chunking strategy.
I have an interesting use case in my org. Recently, they laid off all the Scrum Masters and pure managers, and they came up with a model which reads all the BDDs and identifies the conflicts among all the BDDs. And it automatically generates all the Jira epics and user stories under that from the BDD.
Yeah. Yeah, I know. I've also heard several scenarios where I think the Scrum Master role is the first one to be hit by the AI models,
They're
because
automating all the management work and Scrum
yes,
management and user.
because it is not critical, right? Business critical. Even if an epic is created wrong or a story is created wrong, that does not impact anything in the financial. You can always check manually and then correct it. So I think the less risky ones are being first replaced by the AI. Yeah, that's a nice observation. Right. Okay, so that is the chunking strategy let's talk about. Overlap we are talking about involves adding repeated context between adjacent chunks to ensure continuity and context retention. Okay, so why it matters? It prevents loss of meaning when retrieving or processing adjacent chunks. So if there is no overlap, it may not know that they belong at the same context, same area of the document. Might feel that they are different, disjoint. So overlap will help you to give, hey, these two belong to the same context, kind of a thing. Okay, so the example here is if a paragraph is split into two chunks with overlapping sentences, the first chunk paragraph will be like AI is transforming industries, machine learning. A subset of AI is widely used. So it is cut here based on say characters, number of characters I give it to cut the chunk. Maybe 1,000 characters if I use. So it is cut here, 1,000 characters. Then the second chunk will start from machine learning, a subset of AI from here. See, so this sentence is repeated. Machine learning, a subset of AI, is widely used in predictive analytics. So it will help you to join these two and say, hey, if I want to write about what machine learning, then I have to pick some information from this chunk and some information from this chunk because it is a continuation from here in this document. Okay, for building conversational agents to ensure the agent doesn't lose context. across different terms. Okay. Now we come to the same embeddings. So we have been discussing, so I'll just quickly parse through. We have already talked about it. What is an embedding? It's a dense vector representation of text, images, or other data. So all we have seen right now is only text, but even the images can be done by the vector as a dense vector. So that's how image recognition is done. So all your image is split into bits, and each bit is again converted into a vector, and as a whole, the entire vector is stored, and then it is compared with whatever images you give it to the model. So it will split all of those and compare with this vector and figure out, hey, this image is closer to this image. That's how the image is recognized, image recognition or creation of the images. Enables semantic similarity and semantic search by converting words phrases into numerical vectors, captures meaning, context, and relationships between terms. This is the most important part of the embeddings. It captures not just the text. It does not have a code saying that for A I use 1, for C I use 3, for K I use 12. It does not have such kind of any rules or algorithm just to replace words with numbers. It captures the meaning, context, and relationship between the terms. So example is Apple fruit, Apple company. When you create embeddings, it will differentiate between these two based on where that Apple word has come in that context, in the meaning. Okay. You say if I work I work at Apple, or if you say I ate 2 apples today, these two will have different embeddings for the apple. Okay, so that's what embeddings are, to differentiate the meanings based on the context. And scenario is basically what we have seen to do the semantic search and get the relevant results. So what are the embedding models? As I said, popular models, OpenAI's, Ada, BERT. Every company has one or the other embedding model. Even NVIDIA has model that we have just seen. OpenAI has models. Mixtral has models. Meta has models. And most of the Azure, no, if not Azure, AWS has models. So all of them are equally performant in doing the embeddings. So we can look at what kind of models it is. One second. Embedding models. How many embedding models you have? See, if you see here, VV8 is one of the vector databases. So if you see here, just like models, if you see embedding models, Voyage Large 2, SFR, embedding Mistral. This is from Mistral. I don't know, they have not given from who's the creator of this. But if you see your Voyage Lite, Grit, E5 Mistral, Google, Grit LM, GTE Large, LLM V2 Vector, Meta. This is from Meta. So there are so many hundreds of models that you have. If you go to Hugging Face and then search face. Models, DeepSeek, it's already at the top. I want to search for embedding models. Okay. So if you see here, all MPNet base V2 sentence transformer model, which converts the sentences into embeddings. Just premium. See, okay, there are 1700 embedding models. Okay, Salesforce SFR embedding, Salesforce, Keynote. Sentence transformer, all mini LM L6V2. This is the one that we used in one of our use case in my earlier project where we built the RAG application. So we used this model to do the embeddings, all mini LM V6. Okay. So there are so many, as I said, like there are 1700 models. You can choose any of them. And then if you go here, I was showing you earlier in the data stacks here, and I go create collection. You see here embedding models, NVIDIA. So this is basically AstraDB is using NVIDIA as default. You can do bring my own. Okay. Generate embeddings on your own and import them when you add your data. So if you don't want to use your own model, when you create a collection, you say, hey, use your own model, generate the embedding and store it. So then it says NVIDIA is the provider, default provider, but you can bring your own. Okay. So if you do bring your own, you have to provide all this dimensions and the who's the provider and all of that you have to give. Basically, so NVIDIA is also one of the providers there in that space. So some of them have their own models, some of them have default collaboration with other vendors and use their embedding models as default. Okay, any questions in that? So OpenAI's ADA embedding model, scenarios are all like dimensionality, performance. So all of this we do in the match retrieval is basically, as we see, embedding is to generate the embeddings as a vector. Vector database is to store those vectors. Retrieval is to go search using any of these, cosine similarity, Euclidean distance, and dot product, any of these, to go and search and get the relevant results from the vector database. Okay, so that is the retrieval, match retrieval part. And I said vector databases, you have store, index, and query, Pinecone, ChromaDB, VV8, FiceDB. This is from Meta. Use cases, semantic search. It is used in recommendation engines and the RAG applications. Okay, so that is all theory. Now, we did till now. Now if you have any questions, we'll talk about it. Otherwise, I think we had enough of the things. We can move on to our demo. Okay. Good.
Yeah.
Okay, so I'm using the Google Colab here just to start with basic Python, and we use a FireDB here, Meta FireDB as my vector database, and sentence transformer for the embeddings. All MPNet base V2 is what I'm using the model name for the embedding. So if you see here, it should be available here. So, okay, all MPNet base V2 sentence transformers. So this is what we are using. I'm using here 27 million downloads last month. Okay, so you can just how to use it, pip install sentence transformers, and then import, use the model as the name, like this sentence transformer / all MPNet base V2 embeddings is model.encode, and then you pass all your sentences. So this is where you need to have Python knowledge. Just to understand what is an array, what is a list, how do you create, basic knowledge of how to call a function, what are the parameters, what is the return statement, right? So to that extent, if you know, you are good. So this is the model, and then you get the embeddings, and then you can print the embeddings. So this is the model. So here, what I did pip install FAIS CPU. This is the embedding model is sentence transformers. The vector database is FAISDB that I have installed here. Let me go. Clear all the output.
Where did you create this notebook?
Huh?
Is it in Databricks that you are creating this notebook, or?
This is just Google Colab.
Okay.
Yeah. You all can just go to your Google and just type Google Colab. It will open Google Colab and use your Gmail ID just to log in.
Okay.
This is the easiest and the best Python environment to run. You don't need any. I also have this visual code thing where you can create projects, write and execute IDE. But to start with, this is the best.
Okay.
So first, this is how you will install. Not authored by people. This was authored by Shamim Sheikh. So
You can roll.
Even Python cannot run without the permission. Okay. So first what you do is you install what are all the required the libraries, pip install libraries. I'm using the vector database by CPU and the embedding model. Why I'm installing 5CPU is it's, as I said, it's a file-based vector database. You don't need to go and create a database somewhere or create API key or whatever. I'll come to that in the next use case demo. But for now, for this FAISDB, we can just install that as a volume. Okay, so it will install all of this. Then generate code to connect to store vector embeddings in FAISDB and do semantic search. So we'll import FAISDB, NumPy from, this is a library from Python, sentence transformers that we downloaded for the generation of the embeddings. Now I'm generating some data here, creating some data. I have like 1, 2, 3, 4, 5 sentences. Okay. And you see model is equal to sentence transformer. I'm using this model name. Okay. Or any model that you want that you can use from the sentence transformer. So this is the model. Now I'm generating embeddings, model dot encode. I'm passing this array sentences. Okay. And then numpy dot array. So you're converting these embeddings into a float vector type so that you can go to the index and add the embeddings to the index. So this is all FAIS index. How do you want to fetch? So you don't have to learn all of this. I don't even know what all of this is. The AI will still give you. Okay. You'll get a lot of help from the AI itself. Maybe there will be some errors you need to fix here and there. It will take some time for you to get used to, but most of it, if you want a code, the AI will generate. It will give you the code. Okay, so you have an AI assistant here, Gemini. Basically, this is the LLM model from Google. So everywhere in Google environment you go, there will be Gemini. So you can ask, any help questions. You can ask it to troubleshoot, do whatever here. Okay, so if I go and say generate Python code to connect to FAISDB store embeddings, use sentence transformer model to generate embeddings. Okay, that's it. It's the same thing basically. Install transformers, import sentences, embedding model, shape, write index, whatever index name you give, and then it gave you a semantic search method, where you pass in a query and top k equal to basically how many results that you want. And then you give a query and call that function. That's it. And then it'll also give you why you are doing this at each step. Yes, Pawan.
So Harun, here the chunking is happening within that model, right? Like all MPNet base V2 default chunking settings, whatever that
Yeah,
is
here
there
I'm
in
not
this
doing any
attachment.
chunking. Basically, I'm passing each sentence as a chunk.
Okay, okay, so
The
okay,
chunking is still not there. We'll come to it.
okay.
So here we did only embedding and
Here,
dimensions. How are we selecting
if
dimensions?
you see here in this PDF, I'm loading a PDF and documents and using a character test splitter. I'm giving the chunk size here 1000. Overlap is 0. So there is no overlap. Then it will split the document based on this chunk size, and then that we will use to do the embeddings. So we will come there. Sorry, Hima. Yeah, go ahead.
Yeah, dimensions on embeddings, right? So usually how we will select these dimensions.
So here we are not giving the dimensions. Okay. So dimensions is, you cannot give the dimension. Dimension is what you call hard bonded to the embedding model that you use. Whatever model you are using will come with the standard dimensions. So all MPNet base V2 will be already having the dimensions.
Okay.
So whatever dimensions it has, it will, you have to use that. It will tell you all that thing somewhere here. Just a bit. If you go to the documentation, it will definitely tell you.
I'm thinking whether it is based on the data set size or something.
No, it's not. The data based on the data set size, you can do chunking, but
Okay.
not the
So
dimensions.
it will not have any impact with the number of dimensions we are using, is it?
It will, right? So if you think that your data is huge, your chunk size is huge, and the vector dimensions is not giving you proper response, then you can change the model to go with the bigger dimensions.
Okay.
Okay.
Yeah, the dimensions are mentioned just there on the screen where your cursor is currently. Yeah, 760.
So it maps sentences and paragraphs 768 dimension. So this is a smaller one than what we have seen in this. Here it is 1024.
Okay.
It's stopping again.
Model determines the number of dimensions it is.
Yeah. So the embedding model will decide whatever model that you are using. It will have the default embedding dimensions for the embedding.
Is it based on the dimensions only we select embedding model or any other criteria what embedding model to choose?
Yeah, that's what we discussed, right? Basically, each embedding model again will come with, if it is free, how big it is, what is the volume that you are using, what is the price that you will get, how complex is your data, what is it, the smaller chunk, smaller dimension 768 is good enough, or you want to go with the bigger one. So all of these factors will determine how you choose your embedding model. Okay, just like selecting a product. What is your business use case and what are the available models? Is it actually helping you? So if you want, you can use the free ones. There are a lot of free ones on the Hugging Face that you can use. Free embedding models, open source, or you can choose paper token models if you want a better, more advanced features or the performance or the size of that.
So does it vary depends upon the data source also? From where
No,
the
it's
data.
not right. See, end of the day, you are passing a chunk to the embedding model. It doesn't matter that chunk is coming from PDF or text or database or whatever. That is, you do the pre-processing before sending it to the embedding model.
Okay.
So all the embedding model sees is just the chunk of text. So if that chunk is 1,000 characters, 10,000 characters, 100 characters is what you decide. Okay.
Okay.
Great. All right. So as I was showing you, basically, so this most of this you will get the help from AI. Basically, it's the same thing. I think generated code, but you have to troubleshoot and see if it doesn't run. Where it is going wrong, what it is doing. But at least you should understand why you are using this. Okay. Index. What each line is doing. Flat L2 is a simple index. Consider other options for large data sets. FICE index. Okay. Within the FICE index, you have option of what to FICE DB, what index you want to use to store this dimension and embeddings. So whatever embeddings is based on the model. So it is getting what is the default dimension for that model and passing that dimension to create the index where you store your embeddings. So index is created, and for that index, you are adding your embeddings. Basically, your embeddings is all of this. Okay, that is n-dimensional array, ND array. And that is what you are storing in the index, flattened. So all these 1, 2, 3, 4, 5 sentences are stored in this index and the dimension array. It's going to create and save the array. Once that is done, then you can do a search on the embeddings. So here it is building all the database, tokenizers, generate embeddings, store, all of that. Now it's done. So we are defining a function here, semantic search, to which we can pass a query and pass how many responses that we want to get. So what that function does, model.encode. See, it is using the same model here, whatever you defined. This model is again the same one, all MPNet base v2. As we said, we have to use the same model, encode this query, numpy.array, query embedding. Okay, so once this is generated in the embedding, it is converting into the numpy array and passing to the index to search this query embedding with the top k. Basically, how many results you want. You want the nearest 2 neighbors, nearest 3 neighbors, nearest 10 neighbors. How many you want, closest ones. And then it will return for all of these index, whatever, you're just, whatever response that you are getting from the index, you are returning. Now here, I have a query. Find sentences about embeddings. Okay, so if I run this, it gave me 2 sentences. Each sentence is converted into embedding. Semantic search is performed using these embeddings. What is the distance from your query? So your query is this, find sentence about embeddings. So when this is converted into a vector and compared with these two lines, the distance is 0.5 and 0.8. Okay, so if you come here, in these 5 lines, so we asked about embedding, so it returned this and this. Okay, now I said top k is 2. Okay, so what happens if I change that? Semantic search query and say I want to pass 4. No, I want four results. Now see, you got the previous 2, each sentence into embedding these 2, the distance. Now the other 2 also it gave, because even though it says they are not related, but still you wanted 4. So then he said, okay, take the other 2 also. This is another example. This is an example, but the distance is 1.24, 1.28, which is very far from your query.
Is this what we are calling hallucination, or
No.
is this-
Hallucination is completely different. This is vector search. You are searching for a vector. Basically, see here. And go back here and see here. The distance. Your question is this. Okay. Your answer is this. So it will return this. But I said, no. Send me whatever are closer here, udhar, jo bhi hai. I need at least 4 closest ones. Then he said, okay, take. This is the first one. The next one is this one. Third one is this. Fourth one is this. Take it.
Okay.
I don't care if they are too far away, but you asked me for 4. I will give you 4, but the best one, closest one is this. So that is why it is also giving you a score. So the database, what they will do, some semantic vector databases, they'll give you a score 0.5, 0.8. This is as close to 0. It's a best match or the closest match to your query. Because I asked 4, it gave all 4. So if I ask 5, it will give all 5. Okay. See, now it gave this also 1.32. Now if I say, remember 0.5, 0.8. Now say, hey, give me only one match which is closest to this. So it will give you only one. Hey, this is the closest one, take it. Okay. Now, why do I want more? Right. So this is just, as I shown you, part of the RAG application, correct? So embedding relevant data. Now I have to pass this data to LLM so that it can go through all the relevant data and provide a response. Now, if I am not passing enough information or exhaustive information or more information for LLM to do a, kind of go through all of it and construct the answer, it will only generate from what you provide, right? So if I come here, I want to say find sentences about embeddings. My LLM model should say semantic search, each sentence is converted into an embedding, and semantic search is performed using these embeddings. That is the expected ideal response from the LLM. When I ask a question, tell me about embeddings, right? But since if you restrict the retrieval results to only one, it says, okay, whatever one result that it gave, each sentence is converted into an embedding. The LLM will only know this sentence, so it will only give you this answer, but it will not tell you the other information, how this embedding is used, which is there in the next sentence. Semantic search is performed using these embeddings. So that information is missing because you are not passing it to the LLM. So the LLM does not know. It will only generate an answer based on what you are providing to it. So if you provide only one answer, it will only provide this answer coming out of the LLM. So basically, you have to give relevant results, not too much of, no, if I put 5, these 3 have no meaning. If I put 1, this is missing. So you have to figure out what is the correct number of relevant records that you should get using the vector database. This is also a tuning or lever that you as an AI engineer should look into. what is the best count or number of relevant results should I use? Should I use top 10? Should I use top 5? Should I use top 3? Am I losing some context? So these are the things that you should look at. Hallucination is completely different. Hallucination is like you ask something, it doesn't know, so it will start giving you some gaslight, you give you some irrelevant response or something about it. So that is hallucination. Basically, if it does not know the answer, it will try to fake or give you some irrelevant things. So that is hallucination.
So if you are sending all these 5 sentences to LLM, right?
Mhm.
How it will rearrange? I mean, how it will
So
prepare?
that is up to the LLM how it uses. We don't know. So that's what we have to look at the when you build a RAG application, we can use this example and see how it performs. There's no LLM here right now, but we can build use case or give you that use case to build that RAG and see how it performs. But yeah, high level. So this is how you do. So what we have used here, we have used the FISDB. Okay. Now let's go to another model here, which is called Pinecone. So if we go to app.pinecone.io, this is a company called Pinecone, which has a vector database. So there you can create your login, and then you can create your vector databases, create your indexes, and then use it to call from your application. Now, what you need to connect to this through API is your API keys. So when you go pinecone.io and create your own own account, right? It's a free. You can go and say go to API keys, create API key. So it will give you some key. That key you have to use. That's one. The second key you need is OpenAI. So we will be using OpenAI model as well. So we are using OpenAI here. So you need a OpenAI key. So how do you get OpenAI key is also
In the middle.
sorry.
We lost you for some time in the middle, for a couple of minutes.
Oh, is it? Sorry. Where was I?
Pinecone, you opened it and you said we
So,
can vector
yeah,
database.
Pinecone, you can go create your own account, and then here you can create database and then create an index. Okay. And then to use this index, you have to have a API key to call from your script. So you can go to API keys here and then say create API key and copy that key value, and you have to use in the script. So another key you need is OpenAI key, because you are using OpenAI as well. So you can go to OpenAI. Time I get lost. Okay. So go here, platform.openai.com. Use your login. and you can go and see here settings, API keys, and then create new secret key. So you will get a secret key here. So these are the two keys that I'm using right now to connect to these two models. One is OpenAI, that is as ChatGPT. So OpenAI has some models that I'm using, and vector database I'm using Pinecone. So I need to create this API key. Okay. So once you have login in the Pinecone, you can go database. Okay. And then you can first create a database and then create an index in that. So you can say go create index. So this is your first, whatever project it gives you when you create. So you go to AI agents and then you create your own, test index, whatever. Text index, test index. And then use any of these. So see here, these are all the models that Pinecone already has. First thing. This is from the Microsoft. This is already hosted. They are hosting this. They have a OpenAI models also. We can use text embedding 3 small, text embedding 3 large, text embedding ADA 002. So when you select this, automatically it will tell you what is the dimensions that it uses. Text embedding 3 large, it is using 3072 dimensions, whereas this uses 1500 dimensions. This uses, ADA2 also uses 1536. Now metric 3, you can use any of this to do the similarity search. You can select one of those. And then you can go and create your database, use serverless, use any cloud provider, use US East 1, Virginia, whatever default, and then go ahead and create. Okay. Use basically which one I have used here. Indexes, semantic search, fast I have used. So indexes, this is what I have created. I've used AWS, US East 1, serverless. Model is text embedding 3 small. This is what I have used. Okay. And this is the index name. So this index name and the API key, these two you have to use. And you have to also remember this is the dimension I have used 1536, text embedding 3 small embedding model that is being used. Okay. Now come here. These are all the libraries that you need install. I don't know if I run how long it will take. Run anyway, sir, please. So it will install all these libraries so we can explore. Now this is all you can. I will give you these notebooks, okay? But you have to add your own keys. Now see, Open API key, Pinecone API key. These are the two keys that you need to add as is. So where it gets in the Google Colab environment is, you see here the key, click, and then you add name and the value, what you get from there, and enable this notebook access, these two. Okay. So once you set up these two, then you can get from here, access from here. Okay. Don't hard code that value here, because once you hard code it here, if it is exposed on the net, OpenAI will immediately say it is compromised, and then that key it will invalidate. You have to go back and again create new API key. So use this secrets and create a add new secret. Put this name and keys, whatever you get, store here. All right. Now, okay, so this is successfully installed, all of these libraries. Basically, we'll go later, we will explore what is LangChain, PyPDF and tick token, unstructured, NumPy, Pinecone client, LangChain community. So, Pinecone client, we are using because Pinecone we are using as our vector database. All right. Pandas and NumPy are default, not default, basic Python libraries that we use for data frames and processing the what you call the collections and transformations that we do. So we use this. PyPDF we use to what you call read a PDF, right? And ingest data from the get the data from the PDF, convert the data from the PDF. Tick token is basically again one of those to split the chunks data from this, and unstructured is also one of the libraries to read the PDFs. I don't know why we are using both. We'll just leave it. OpenAI, because we are using OpenAI model to embed to do the embeddings. LangChain is basically a framework to connect all of these components. It's just like a orchestration to join all of this. So we will discuss LangChain, LangFlow, LangSmith, all of these in our next sessions. Okay. Once these libraries are all installed, okay, you don't need to anything. Google Colab will take care of it. Just add it and run it. Import all of this. LangChain, in the LangChain, you have OpenAI embeddings, which will use the OpenAI, whatever that we are using to generate embeddings. Character text splitter to split the text. PyPDF to load from the PDF documents. And then Pandas, NumPy. From Google Colab, you're getting these keys from here. And you are adding it to the environment variables to use. I think it is in the circular. I didn't check why we need to do this because it is working. I left it. Pinecone, import Pinecone as Pinecone client. So there is some confusion about the Pinecone client that we are using. So I had to do some debugging. But basically all of this is just using the downloading the Pinecone client to talk to the Pinecone and provide the keys to it. Okay. Now here is our processing where it starts. Now coming back to our this thing. So this is where it all starts, right? You read raw data, PDF data. You do extract information, chunk, embed, put vector database. So let's see how we are going this in here. I am creating PyPDF loader with the file path, whatever the file path. So I am using this file path. I have to upload that here in the files. I have to go and upload whatever file that I have here. What files? I tried with some of these. You can try this, but I will try after I explain. So right now, if some of the PDFs it's having some issues. If it is basically I have generated those PDFs, so there is some corrupt, something is corrupted in those PDFs. But I used my resume, whatever PDF content, file path, documents loader dot load. So the loader will load this file into documents, and then I use character text splitter. So I am giving a chunk size of 1000. So each chunk will be 1000 characters. Okay. So whatever it runs, it will run for, it will get for 1000 characters. Overlap is 0. So there will not be any overlap. Text splitter dot split documents using. So I pass this text splitter with these parameters. And then I call the split documents method on this and pass whatever file that it has loaded. So this is all basic Python. So this is pre-processing that we are doing for the RAG application. Okay. So then now this docs is all chunks. Okay. It's an array of all the chunks. The document is read and split into the chunks. Now, if I go to embeddings, I'm creating a OpenAI embeddings object, okay, class. So here it will automatically use our OpenAI key. So that you have to read from here and set it in as the environment variable. And then doc searches pinecone dot from documents. So I'm passing all my chunks, docs and embeddings object, which is OpenAI model that I'm passing, and the documents I'm passing, and I'm giving the index name. So basically it will use this model to generate the embeddings for each of this document and then store it in this index name, doc search. So that is where we are adding to the doc search. So I'm just calling this method using the index name that I have created. So it will automatically again use the Pinecone API key to connect to the Pinecone environment database. So take this index name, file path, and run the add to Pinecone. So let me run this. Okay, there is no file path. So there is no file. It's throwing error. Now let's go here and add a file asking for this PDF. Deleted. Okay, fine. Once your runtime is done, you close this. All this is a temporary storage, so it will go away. So you can again go and add it later. So I have loaded this. Now I can go back and run this. What happened? Valid file. Oh. Then you see a file which has no space. Yeah, this one. I will run this. Deprecation. OpenAI embeddings was deprecated in LangChain. We have to use the other one. Okay, fine. Deprecation is fine. Okay, so this is run. Okay. Now I will go and run the query. So queries, what are the certifications from the Pinecone thing? So see here, it gave me the certification and badges from the resume. Databricks certified, GenAI associate, this. But then my chunk size is 1000 characters. So it gave everything, whatever is there, where it found the certification and badges thing. Okay. I don't know why it is repeating 3 times. Maybe because it has found 1, but I have given k equal to 3, top 3. So it's trying to read that and get the same. So let's put k equal to 1 and search. Okay. So it just gave me certification and badges from the PDF. See, I have so many things. I'm so proud of my resume.
We too.
Yeah, it's very heavy.
You have it.
Okay, so this is how basically your database, your embeddings and vector search works. Now, if you want to go here look at the index. This is where you have written that, right? So here you can see all your records that were stored here. So you see here in the vector database, from there you have written score, ID, this is the values, metadata, this is the chunk, text, okay, and these are the values.
So each chunk will be divided equally, or it will format it?
1,000 characters, right?
Okay.
So each chunk will be 1,000 characters. And then whatever overlap, if you give 0, it will be 0. So record count, basically record count is 27. 20, there is 27 records. Don't worry, just say list fetch. So here, so these are all the records.
So under namespace here, we directly create indexes, not vectors.
No. So index is basically more like your database. In the database, you create multiple indexes.
Yeah, and database, maybe it is the
So
name.
this is one index. Within that, all your data will go. So you can have another index within the same database called AI agents or database. It's all semantic. Some call database, some called schema, some called collection, some called index. See, so here it is index. Some other databases call it collection. We have seen right here. There is that Astra DB. Here it is called collection. Okay, create collection, and they call it here create index. And in Databricks also it's called index. Okay? Some people collection, some people index, but basically it's the same thing. It's like database and schema where you store the vectors. So this is one collection. The point here is you can have different indexes within the same database which use different models and different dimensions.
Oh,
Yeah. So each index is different. If I create another index here, I can use a different model and different dimensions, everything. And whichever you want to write to index. So you can have some data written to an index with a smaller dimension, some data written to a bigger dimension, kind of a thing, based on different use cases.
yeah,
Just
and
one you can.
it will pick the same embedding, right? Again, while querying, it will use the same embedding whatever we have chosen while creating the index, right?
Yes. So if you want a bigger an index with larger dimensions, so here I can use E5 large for this. Or 3 large, so 3,000 dimensions, and create a new index. And then some data I can write to the previous one, right? And some data I can write to the bigger one, 3,000, based on my use cases. It's basically like you have different schemas, right? So you can create different indexes. Okay, that concludes our vector databases and embeddings. I think we had done a lot of learning today. I'm sure most of you are overwhelmed, but go through the recording, take these 2 use cases. I will publish the notebook. Okay. Tomorrow we will have hands-on lab. You guys do.
Maybe you revise once again on all the different embeddings that we tried.
Sorry?
Different. Maybe we will have to again review all these.
Yes,
different-
definitely. We will review tomorrow. We will have hands-on. By that time, you guys set up your Google Colab, set up your Pinecone account, set up your FiceDB. You don't need, just Pinecone and OpenAI. These 2 keys. I will publish the notebooks, or you can use AI also to publish, but you might hit some errors. But I will publish these notebooks. Tomorrow we can do a hands-on, try to get some new files in here and try to run these. And there are more, vector databases. That ChromaDB is one thing we can explore. So I will show you the Databricks one tomorrow. And then we do some hands-on. So tomorrow we will spend time on these same embeddings and vector database to refresh and review. And then that's the part one. Then we will go to RAG later. Okay. And then we will see how we progress towards the weekend. We can complete, or we want to extend it next week so that you all have time to go back, review, explore, and then do some hands-on work. We'll plan accordingly. So we'll see tomorrow and Thursday how it goes, and then tomorrow we'll plan. Is that fair? Everyone? So, okay, how do you feel? It's all good?
Yeah, it's all good, Arun. Only thing is, yeah, as you said, it's overfeeding today for us. I mean, for me at least.
I know. That's what I said, like even tomorrow.
Because it's an entire world for me. So
Yeah, tomorrow again we will review and redo, but it'll be really helpful if you go and review this video recording tomorrow in the daytime, anytime before 7:30 we meet. It'll be helpful. If not, again, yeah, we will do a review, we will do hands-on, but at least make sure you have Google Colab environment, you have the keys, or we will create keys tomorrow. Just check that out. We will do hands-on lab tomorrow, all of you. You can do the session, can share the screen, run and see things. And based on how it goes tomorrow. So tomorrow, that's why I'm not going to start the next topic until we are comfortable with this. Then we will go to the next step of RAG applications, because it will get more complex going forward, building RAG and building agents, agentic AI and all of that. But yes, since it is a boot camp, it's not like full-fledged training course. So things will be a little at a faster pace. But this is just to give you a comfort factor for you, so that you are ready to explore on your own. But we'll make sure that you are all comfortable. Okay.
yeah, and one more thing, Arun. So first, the diagram you showed that we do the split, right? The split is nothing but the chunks what you did in that example.
Yes, exactly. Split is just chunking.
Okay. So that we had to do as per our data and as per our
Yes.
how much we are. It's
Yeah,
not
that's
the
what we
system
have
which is
done
there.
in the code, right? I will also
Okay.
publish the presentation that I have shown, right? The deck. I will also share that.
Okay. Yeah.
Harun,
Okay,
has
then.
to count on Databricks Community Edition, or do we need cloud version?
Oh, we need personal community edition. You cannot. It does not have the vector search enabled on the vector databases. So we have to have our environment, Azure Databricks environment that we need to configure. That's okay. I mean, you don't need to practice on Databricks right now. If you practice other use cases, that should be good. But if you want, you can explore that as well. I mean, Databricks Index is also one of the vector databases, but if you have FizeDB, Pinecone, ChromaDB, it should be good. I mean, they are all the same anyways. AstraDB data. Okay. Ramya, I know you will be overwhelmed, so don't worry about it. We'll start from the data engineering, and then we'll get back to this later.
Yeah, sure.
Yeah, Pavan, Raju, Subbu.
Yeah, I joined later.
Yeah.
So I try to understand, so overloaded today technically.
Yeah.
Tomorrow, definitely, I will go through daytime after you post recording thing. I will go through that one. And yeah, I will attend tomorrow lab.
All right, folks. Thank you so much. We are 4 minutes over. I think we are pretty good at time, managing the time. Yeah, well, good. Have a good night. Please review. We'll meet tomorrow.
Yeah, thank you. Bye.
Okay, thank you so much. And please provide your feedback if you want anything else to be improved. Please feel free to communicate. Okay, thank you. Take care. Bye.
Bye.
Good night.
Thank you. Bye bye.